All right, day 10. We're back. I've got some coffee. Now, we've got a private leaderboard. The problem has been up for 1 minute, so I don't think anybody's done today yet. Or actually, maybe somebody has. There's a 1 there. I don't know. But this is what the community leaderboard is looking like. So congrats, Talk Lime. And we got quite a few people on it, so nice. Welcome, everybody. Let's take a dive into day 10. I think we were falling from a bridge in the last day, so we avoid the ropes, plunge into the river, and swim to the shore. How exciting. The elves are yelling at you. The river's loud. We got to replace the video system for our communication device, it looks like. Ooh, this is the CPU instruction episode of Advent of Code, it looks like. Start by figuring out the signal being sent by the CPU. The CPU has a single register X, which starts with the value 1. It supports only 2 instructions, add X and no op, or noop. Add X V takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. Noop takes 1 cycle to complete. It has no other effect. I hope those are sequential. The CPU uses these instructions in a program, which is our puzzle input, to somehow tell the screen what to draw. So we've got no op, add x3, add x -5. So first cycle, x is 1 because x gets set to 1 by default. The cycle finishes, the no op does nothing. Second cycle, add x begins execution. During the second cycle, x is still 1. During the third cycle, x is still 1. After the third cycle, the add x3 instruction finishes, setting x to 4. At the start of the fourth cycle, the add x -5 begins execution. So they are sequential. That's wonderful. So this is 1 cycle, 2 cycles, 2 cycles, and we end at 5th cycle. So we're supposed to look at the value of x throughout the execution. For now, consider the signal strength, the cycle number multiplied by the value of the x register during the 20th cycle and every 40 cycles after that. Okay, so we've got a larger program here. It's quite a bit longer. Interesting signal strengths can be determined as follows. During the 20th cycle, register X has the value 21, so the signal strength is 20 times 21 equals 420. Yay. So signal strength is 20 times 21 is 420, but the 60th cycle, register X has the value 19, so it's the 60 times 19. So these are all signal strengths, and we need to sum them up. Okay. Find the signal strength during the 20th, 60th, 100th, 140th, 180th, and 220th cycles. What is the sum of these 6 signal strengths? Okay, interesting. So we can get started pretty quickly here with the parser. The parser is going to bring in a no op and an add x. I think that'll be pretty easy for us to write. And then we'll write an interpreter, probably on the instruction set. We'll also say like get num cycles or something like that. And we'll loop for a number of cycles. And then we'll do the thing that we're supposed to do. I suppose it is possible that we don't have an instruction executing on each of the cycles that we need to care about, but I'm going to care about that problem later probably. So let's get started with the small stuff. We got no op, add x3, and -5. This actually doesn't give us a testable thing though. So we need actually the longer input because otherwise we don't get any particular value that matters. So we're going to take a nom parser as per usual. I'll name this instruction set. We're going to do a separated list for new lines. And then we need to either parse no op. So we'll do alt with a tuple inside of it, tag no op dot map. Don't care about the tag. And then this is going to be instruction. Actually, we're going to use. So I'm just going to type no op here. And then we need an add parser, which is going to take the input as a string slice. It'll return the rest of the input as well as a instruction. We haven't made the instruction enum yet. I could do that right now. So we're going to do enum instruction. We'll get no op and add. Add is going to have an I32 in it. And then we actually don't need this parser. We could do, I think it's preceded. So preceded lets us put a tag in the start and then tag it. So if we have some input and we do preceded tag AB, tag XY, then we will get back okay with AB taken off, XY taken off, and XY returned as the value. So we'll do preceded, tag, add X, space, complete I32, I think is what we want. And then we need to map over this. We'll map with the num, and then we'll say add the num. Preceded needs to come in from nom sequence. And this will be a vec of instructions. And then I've left this for last. So we get no op and add here, but we want to access them as the names no op and add, but we can't do that yet. So we need to use instruction star. So if you're newer to Rust, this will look a little bit weird because you'll say, hey, I thought that was the import syntax. But realistically, these are not imports in the sense that they are in other languages. Like you can think of them as imports, but they are really just module path shortening like items. So if we wanted to access the instruction here, for example, we could do instruction : no op. And this is a module path from the instruction type to the no op variant. And that would work. So it's the same thing for this and this name that we have in scope, as well as, say, a third-party crate like nom. We could access something like we do here as complete I32 or nom character complete I32, or we can have this use item that shortens the import or shortens the name we need to use by using nom character complete self, which allows us to use complete I32. So we just returned the vex there. Something is wrong currently. What's the type here? Vec of instruction. Oh, right, because I didn't remove I decided not to do this add parser. So this is going to be a vec of instruction. So we get instruction set parsed out using all of the knowledge from the previous days. So we get a separated list separated by new lines. We either get a no op or an addx. The no op is a tag, so we match exactly NOOP, and we map over that to return the no op variant. And then the other parser that could succeed is a preceded, which allows us to take addx space followed by an I32, and we map over that as well. And we use the number that we parsed out and we throw that into the add variant. So we've got our instructions, and let mute x, I suppose, equals 1 for instruction in instructions, instructions.iter, of course. Then we'll match on instruction, fill the match arms. We've got no op and add. We've got a number to add. And then one thing that I want to do here is we're going to write a custom impl block for instruction. We're going to call this cycles. We're going to take a reference to self and return, what did we call so x is 1, and we'll do let mute cycles equals 0 we start with. But this is going to have to be what, like an I32? No, a U32 I think we can use here. So we'll return a U32 here. And if we match on self, we also get no op and add, which allows us to return 1 for no op and 2 for add. So this is how many cycles each instruction takes. And we just got this nice mapping. We can call this function whenever we want. So addxv takes 2 cycles, and then no op takes 1 cycle. We could do a whole thing here where we came up with like a computer struct and then interpreted each of the commands, but we'll probably need to do that later anyway, so I'll do it manually first. I say we'll probably need to do that manually later because that's how Advent of Code works. So we've got our X number and our cycles number. X needs to be an I32, so we'll just specify that right away. We match on each of the instructions. No op is just going to be cycles plus cycles. This return value doesn't need to be anything. Plus equals, right? Cycles plus equals instruction.cycles. And then if we do the same thing here, plus equal instruction.cycles, and then x plus equals num, and it just goes through all the way, and then we get x and cycles. And then I keep to do here because we're not done yet. So let's go and run cargo watch test. We should have 1 being ignored. Part 2 is being ignored. 1 is failing, should be failing. So we've got 17 for x and cycles is 240. It doesn't look like we get the ending value here, so we don't know if that's correct. These numbers feel pretty arbitrary, 20, 60, 100. So these are the cycles that we need to like track. So I'm going to drop these way up here. Let notable cycles equals each of these. Instruction.cycles is going to be either 1 number or 2 numbers ahead. We know that right now, but we won't know that forever. And we do need to do this addition either way. So maybe we take this out completely. We do that addition outside of the match. So the instruction is happening after we've done the cycles. And then we can do something silly like instruction.cycles and cycles ... instruction.cycles. We're going to need to add cycles plus instruction.cycles. I want to make this a range because I feel like in part 2, it's going to matter. So my guess is we get another one, But for now, we can do cycles plus 1. So we could do notable cycles contains cycles plus 1, then cycles plus 1 times x, right? And we need somewhere to store these. So let's do, we're going to do the B tree map again. So let's make this scores, I don't know, equal, which is a B tree map from what? Cycles is going to be a U32, and the value is going to be an I32 because we don't know what it's going to be necessarily. And then we'll initialize with B tree map new. So what we get here is scores.insert. Oh, we didn't import B tree map. It's going to yell at me immediately. B tree map. So it's going to be scores.insert cycles plus 1, and then this value. Of course, we are watching. So what do we have here? I32 found U32. Cycles is a U32. X is an I32. So we're just going to, I think we'll do as I32 here because we need the result to be an I32. I don't know why. Consider borrowing here. Found a reference to an integer. Oh, this whole thing. Gotcha. It's a little awkward, but it's fine. Cannot borrow is mutable because we didn't specify scores as mutable. So really, if we ever get something that's more than 2 here, we can do a for loop from current cycles plus 1 to the cycle length. And then this will be this. And then we will do the same thing down here, but it will be actually cycles. And it's not going to be cycles plus 1. It'll just be cycles times x. And it runs. So let's see if we get our scores. See, 420, 1140, 1800, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that's the right. 420, 1140, 1800, 2940, 2880, 2940, 2880, 4180. 4180 is wrong. 2880. And this is 4180. 4180 is wrong. Why is 4180 wrong? Cycles equals 0. So what's the problem? I didn't read this wrong, did I? During the 220th cycle, register X has the value 18. So the signal strength is 220 times 18. Oh, it's at the end of the cycle. So if we land on 220, then we still do the original insert here. Okay, that's got to be at 420, 1140, 1800, 420, 1140, 1800, 2940, 2880, 3960. So no matter what, if there's a cycle that we hit, then we execute the insert and then we add, which requires, okay, well, if that's the case, then that's the case. I'll get rid of all my debugs here. And then this is scores.iter. What map is going to be key value. And then it's just the value dot sum dot, and this is going to be like a U32 or something. I32 because we have negatives, and then toString. And we'll throw a little underscore here on the key because we're not using it. And then the number is 13140. So this test is that, and that works out. So we can grab the puzzle input, put it in the input, which I didn't do just now. Get rid of that no op output, and then we get 14060. Great, right answer. Gold star, part 2. So the key here is that add x takes 2 cycles, and then that means if we are at 1 and we have to do 2 cycles, then we're at 2, and then we're at 3. But if we hit the 3rd cycle, and that cycle is the number that we care about, we haven't added the number yet, even though we are, quote, like in that cycle. So after this number is added, if we are at the right number to add something or insert something, then we insert the old number and then we set the new value. So a little bit of extra code, a little bit of extra debugging, but process part 1, we get the notable cycles 20, 60, 100, 140, 180, and 220. I just wrote them in manually. We get scores, which is a B tree map of U32s and I32s. U32s are going to be each of these notable cycles. I32s is for the value that we calculate. I'm keeping that information around so that I can debug it out later, which I actually did end up needing to do to check to make sure that we were calculating and capturing the right things. Otherwise, we could just treat this as like a I32 and just keep adding into it. But I wanted more debugging output. I wanted to be able to know which ones we've stored already. So instruction sets is a parser. It's nom again. A separated list 1 by new lines. So we get each of the lines. Then we can alternate parsers. We either get a no-op or we get an addx. If it's a no-op, we map over it and we get the no-op variant from our instruction enum. If it's an addx, then we parse the I32 because we're using the preceded tag. And then we map over that to use the add variant. We've defined our enum up here with no op and add variants. We've also used the use syntax to let us use no op and add on their own without needing to prefix it with instruction. We've used a custom impl block to get the number of cycles that we're supposed to iterate for each of the instructions. This is a match on a reference to self. So no op is 1, add is 2. Then we set up our x variable. This is our number that we're adding to if we have to add. Number of cycles that we've run. This is 1 for a no op and 2 for an add. We iterate over all of the instructions. If any of the notable cycles includes the current cycle or the next cycle, then we insert at that number. And specifically, we insert the cycles that it is at, so 120 or something, times the x value that is already stored. Then we add the instruction.cycles to cycles, and we move on with our day, adding num to num. Once we're done with that, we get the B-tree map, we iterate over it, we map over those values to get the value out, which is just a number. We sum that into an I32 because it could be negative, and then we toString it. So for part 2, it seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. In this system, there is no such thing as a vertical position. If the sprite's horizontal position puts its pixels where the CRT is currently drawing, then those pixels will be drawn. Your count on the pixels on the CRT, 40 wide and 6 high. The CRT screen draws the top row of pixels from left to right, then the row below that, and so on. The leftmost pixel in each row is in position 8, and the rightmost in each row is position 39. Like the CPU, the CRT is tied closely to the clock circuit. The CRT draws a single pixel during each cycle, representing each pixel of the screen as a hash. Here are the cycles during which the first and last pixel in each row are drawn. So the cycle from 1 to 40. Okay, so the special numbers that we had before are just the ending cycles, but this draws basically a bunch of pixels. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel, otherwise it's a dark pixel. Okay, so we've got a 3 pixel wide sprite no matter what, right? And our X position is just the position on a potential screen. We keep that in terms of an I32, so it could be like off the screen to the left is my understanding here. Sprite position, start cycle, begin executing add x15, CRT draws pixel in position 0. So cycle 0 is position 0, cycle 1 is position 1. Is that accurate? So we start cycle 1, begin executing add x15. Add x15 takes 2 cycles. During cycle 1, CRT draws the pixel in position 0. So the CRT is looking at 0, and our sprite position is currently 1. So it takes up position like 0, 1, 2. So because we're looking at 0, we have the sprite overlapping with where the CRT is looking. During cycle 2, which is the second cycle of addX, the CRT draws the pixel in position 1. The current CRT row, because we're at 1, draws the second pixel here, which is highlighted because we haven't moved it yet. And at the end of that cycle, we move it. And then we draw position 2, and so on and so forth. And we do this in loops of 40, basically. Allowing the program to run to completion causes the CRT to produce the following image. It's this image. Render the image given by your program. What 8 capital letters appear on your CRT? I hope it's not asking me to read letters out of whatever is shown here, because I can't read any letters out of this. This is definitely one of my problems every year. There's a problem like this that we need to print out, and then the pattern of printing isn't necessarily readable or identifiable. So we have to print this out, and then we also have to guess the characters. Okay, so X is always handled for us, and the pixel we're drawing is in loops of 40. So cycle 1? That's not cycle 1 though, is it? I guess we start cycle 1. So let's copy and paste here to get our part 2 starting. And then let's find what's the answer for our tests. Our answer for our tests is nothing we can test. Actually, it's this, right? Okay, so we should get that output. I'm assuming that we're still testing against this test. Add x15 is the first one. Add x -11. So we are still working with this test input. Okay, so we now need another variable here. So let mute CRT pixels, We could do this, I feel like, in one of two ways. Every individual cycle we do need to draw. So instead of inserts, we'll comment these inserts out. So I think scores don't matter anymore. So we're just going to make this a vec. And this is going to be a vec of string slices, I think. So we'll need to mod the number of cycles that we're at to compare it to x. So cycles mod 40, I think, is the right calculation. That'll give us the remainder. So if we're at 0, we'll get 0. If we're at 20, we'll get 20. If we're at 60, we'll also get 20. Wait, is mod the right calculation here, actually? Now that I think about it. It might be rem instead. So let's go Rust Playground. Let's do just a couple of debugs. And if we run this, 1 mod 40 is 1, 20 mod 40 is 20, 60 mod 40 is 20. So this is the calculation that we want. But this is going to be cycles plus 1. So let's do 4 0 dot dot cycle 0 dot dot instruction dot cycles, right? 0. Let's do 1 dot dot equals for pixel in 1 dot dot equals instruction dot cycles. That's not pixel actually. What should we call this? 1 dot dot equals cycles. We'll do cycle add. We either add 1 or we add 2. We don't need to do notable cycles contains anymore. We need to do cycles plus 1 mod 40. And we need to do x minus 1 dot dot x plus 1 dot contains that calculation, right? This needs to be wrapped in parentheses. I think that this is going to be a reference issue, or no, this is going to be a, we'll let the compiler tell us, but it's going to be a expected I32 found U32 issue. So this is going to be as I32 and it's a reference. So we need to dereference it. Or maybe I was reading this wrong. Cycles is a U32. We need to convert it. We need to add to 1 mod. Type U30. Is this already a U32? That's already a U32. What's the problem? Oh, contains expects the reference. Right. That makes sense. So we wrap this whole thing and we reference it. Numbers are a little bit awkward sometimes if you have to convert between a bunch of things. So for cycle add, this is going to be this plus cycle add mod 40. Is the type of this expected? Okay, that's fine. We can just cast them both to I32s. So if this is all true, then this is the pixel, right? So let pixel ID equals this. Makes it a little bit easier to read and write. This is the sprite width. So it's x minus 1, x plus 1, because x is the index in the middle. So if that contains the pixel ID, then CRT pixels at, is that right? The number of cycles is equal to the CRT pixels. We're not even running our part 2 test right now. So let's start running our part 2 test. I feel like this is going to be an off by 1 kind of thing. Index out of bounds. The length is 0, but the index is 1. Ooh, right. Darn. So we want to be pushing into this is what we want to be doing. So let's do this. Let's do CRT pixels dot push our string slice else CRT pixels dot push dot. And I think that'll run every cycle. Left is 0 and right is whatever. Why is left 0? Because I'm scoring and summing. Let's do CRT pixels dot toString. Oh, that's not right actually. CRT pixels. So I changed it to be a string. So CRT pixels is a string now. Because it's a string, we're doing empty string dot toString, and we can do CRT pixels dot push string whenever we want to do this instead of push, or push str because I want to push in string slices. And then we'd say CRT pixels. We're going to need something like split n 40, right? I'm going to need the classic intersperse. Actually, we can just use join. We don't need intersperse. So we'll join it with a new line. Split n is probably not what I think it is. So we go to split n in the docs, created with the method split n, an iterator over substrings of the given string slice separated by a pattern restricted to returning at most n items. If n substrings are returned, the last substring will contain the remainder of the string. So I think that's right, actually. So if we do split n3, that is not what I want. That's the number of items we're going to get back. Okay, so that's an interesting function. I don't think that I've ever actually wanted to use that function before. We do need some kind of split though. Chunks would work too. We don't want to split on a particular character, so split is not what we want. We really want chunks, I think. And now that I think about it, splitting or chunking a string does feel a little bit weird. So let's do not dot chunks, dot cars, dot chunks 40, dot map chunk dot, we'll into iter, map over it to make a chunk of cars, chunk dot collect. I think we don't need to into iter this inside of it, but we can collect into a string, join with n, and then we get back this output, which is not correct. Wonderful, wonderful, wonderful. So I've done something wrong here. So it should be on, off, off, on, off, off, on, and it's not. So let's debug. Let's print line for a little bit more control over what's going on here. Pixel ID, cycles, cycles add, cycle add. Then we get a whole bunch of stuff. So we never get to 40, which I don't think that's our issue, but we don't start at 0 either. What should we be looking for? We should be looking for the first cycle draws a pixel at position 0. The second cycle draws a pixel at position 1. So maybe it's more like this. It starts to look closer. Okay. So we're at 0, 1, 2. I think we get to 39. I feel like this needs to be 40 at some point. 0 through 39. Oh no, it's cycle 40 is pixel 39 because the cycles are 1 indexed. So these are the cycles. This is the pixel ID. If the sprite covers the pixel ID, we push a hash. Otherwise, we push a dot. So let's do, so we are now pushing out individual hash and dot. And here are our X values. So 1, 1, 16, 16, 5, 5. So 1, 1, 16, 16. So we go off the rails on 1, 2, 3, 4, 5, 6, 7, 8, 9. I think on the 10th pixel. So at 10, we think we're 13. So at 10, oh, it just stops telling us. No, we think we're 13. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're actually wrong at 9. Let's do pixel ID plus 1. Can we do that in there? No. So here's the actual pixel ID. 1, 2, 3, 4, 5, whatever. 10 is this. So hash hash dot dot hash hash dot dot hash. Hash should already be there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. CRT draws pixel in position 10. But there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pixels here. Oh, we're calling this 0 indexed. Okay, great. Wonderful. Let's forget about that. 0 through 10. 10, we're on this, though. So we have to be on 9 to check. CRT draws pixel in position 9. Register X is 8. Register X is still 8. Register X should be 8 at 9, which should match 8 at 9. Should match and doesn't, because we're pushing all of them regardless, I think. If X minus 1, X plus 1 contains pixel ID, so that's 8 minus 1 is 7 plus 1 is 9, dot dot equals. I make that mistake a lot in these problems, actually. That's not the first time I've made the inclusive range mistake, which is really unfortunate. So we are getting the output that we expect. So now we have to run part 2, and we're supposed to read this. So I think this is PAPKFKEJ. PAPKFKEJ. I think that's my input. There are at least 8 letters. Yeah, gold star. Okay. So my only issue was the range. So we get rid of notable cycles and scores in this iteration. So part 2, we have to push these strings on for each of the pixels. So we parse the instruction set the same way we did in part 1. We still have X, we still have cycles. We now also have a string that represents every pixel on the screen. And I've chosen to represent it as a single string just because I found it easier to think about. But you could do a vec of X or a vec of strings or whatever you wanted. So for every instruction, there's a number of cycles that we need to add and test for. So if we're on a no-op, this is 0 to 1. If we're on an add instruction, this is 0 to 2. So we'll get either 0 or 0, 1. Now, the pixel ID is calculated from the number of cycles that we start with, plus the number of cycles we have to add for each of these instructions. And then we mod this by 40, which will give us a wrapping value of 40 over a single pixel line. So the way that this is set up, if I click back in here and we scroll really far. So the way that this is set up is this is like 40 pixels and we only have horizontals. So if you imagine this is 40 pixels, our X value is the center of this 3-character sprite. This 3-character sprite moves left and right here on an infinite number line. If the pixel that we're trying to draw and the sprite happen to overlap, then we draw a positive pixel. Otherwise, we draw a dot. So if the number of cycles that we're on, so we can calculate the pixel that we have to draw by the number of cycles that we're on, because all the CRT does is moves to right and then wraps around and moves to the right again. So this will draw from left to right here, and then it draws from left to right here. So we need to, when we hit 40, wrap around back to this spot. When we hit 80, we need to wrap around back to this spot. But we're always thinking about like a 40 width number line. So the pixel ID is that number. It's a number between 0 and 40, so 0 to 39 inclusive, calculated from whatever cycle we're on. So we create the sprite width by doing x minus 1 and x plus 1, because x is a position on the number line. So this gives us the place to the left, the center of the pixel, or the center of the sprite, and the place to the right. If any of those 3 places contains the current pixel that we're looking at, then we draw a positive pixel. Otherwise, we draw a negative pixel. And we use push str to push onto the string because this is a mutable string that we can do that with. And you'll see that by using push here on the string, I don't need to think about what layer we're in, because you can think of all 40 layers or however many layers we need. In this case, it ends up being 2, 3, 4, 5, 6 layers total. You can think of those 6 layers as being one really long line. So if we just keep pushing on, then we can deal with cutting it up to display later. And then I don't need to worry about which vertical layer we're in at all. I don't even need to do that calculation. Then we finish the cycles off. So we add cycles and we execute whatever instruction we need to execute. It's either going to be a no op or we're going to add a number to X, and then we repeat until we fill out all the pixels. So now that we have a string, we can take all those cars, we can do chunks of 40 of them, we can iterate over those chunks. Each of these chunks is going to be a chunk of pixels, or a chunk of pixels, which are characters for us here. So we can collect those into a string, we can join those with a new line, and that gives us the full new lined output that we can print out. So I do think it would be interesting to implement this as kind of like a display or a CRT or a computer that accepted these instructions. So I might do that in a refactoring video tomorrow. I have a feeling that we'll see this problem again, that we'll see the code that we wrote here again. So I kind of do want to clean it up to make sure that it's usable in more situations with maybe more instructions or whatever we're going to do in the future. So I'll think on that a little bit. And otherwise, have a great weekend, because it's the end of Friday for me. I don't know if it's Saturday for you, but I hope you have a great weekend, and I'll see you in the next video.